Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 21, and in this one we will be concentrating on the topic of bandgap at low temperature. The motivation for this lecture is primarily to explain to you that with varying temperature, if the bandgap changes and if it changes so, then what does it influence on the overall device characteristics and therefore its influence on the threshold voltage of the device. So, primarily the whole story is we relate the change in the band gap with temperature and then relate that to the change in the threshold voltage of the device of a bulk MOSFET, right. So, the outline of the talk, we will be looking into a model known as Varshni model, which is basically a model which takes care of the change in the band gap as a function of temperature. We will look into bandgap widening, part of the Varshni model at cryogenic temperatures, and then we will look at the physics of the device at cryogenic temperatures. So, in detail what we will also look into is the variation of threshold voltage. So, I will take up a sort of a research paper, and from that paper we will try to give you an idea about how the experimental facilities are developed and how the measurements are done at cryogenic temperatures. Now, this we have already discussed in our previous lecture. The Varshni model for the temperature dependence on the band gap is given by the statement shown here, right. This is the statement which is given here, where EGT is basically the band gap, the EGT is the band gap which is there. So, EGT is the band gap which you see here, and this EGT is basically the band gap at temperature T as a function of temperature T. So, what you can do, T is varied from 300 Kelvin and it goes down to up to 4 to 5 Kelvin, right, 4 to 5 Kelvin. So, this is the variation which we do. EG0 is basically the band gap at T equals to 0 Kelvin, and then we have a function of temperature with a negative sign, which primarily means that as the temperature goes on increasing, the band gap starts to reduce, right. So, the Varshni model actually takes care of the fact about the band gap energy change with respect to temperature. EG0 is basically the band gap at T equals to 0 Kelvin, and it also depends in a sense inversely on the value of T and therefore a T here. So, as the value of temperature goes on increasing, since it is a T square dependency term coming at the top, at the numerator, this quantity actually starts to grow with respect to temperature, and therefore, this quantity, since subtracted from EG0, you see a dip in the value of EGT, and that is shown here in this graph. So, if you look at the graph on the left hand side, which plots energy band gap versus the temperature, absolute temperature in Kelvin, then as the temperature goes on increasing, the value of the band gap actually in electron volt starts to drop down, right. And why is it important to showcase this one? Because this will indirectly affect the number of charge carriers being promoted to the conduction band, and which indirectly will change the threshold voltage of the device. Alpha beta values are taken empirically in a sense to match with the experimental data. So, that is what I was trying to say in the previous slide, that the band gap increases from 1.12 eV at 300 Kelvin to approximately 1.16 electron volts at 4.2 Kelvin, right. And band gap widening therefore takes place as the temperature goes on decreasing, and therefore, as the band gap decreases, the threshold voltage will go on increasing, right. And the reason is because you require more band bending is required to reach the inversion. What does it mean actually? You see, if you widen your band gap, right, if you widen your band gap at lower temperature, then when you apply a bias on the gate side of a MOSFET, a positive bias, the electron energy will actually dip down, right. So, I do have a possibly I can show you one PPT, maybe I do not know, it is right. You see, on the metal side, if you start giving a bias here on the metal side, this actually bends down, you see, this is bending down. Now, if you had actually increased the band gap from a low value to a high value, then for inversion to occur, you have to bend more in order to have large number of carriers available at the conduction band. And that is the reason your threshold voltage actually becomes much larger in this case, and therefore, there is increasing. When the threshold voltage increases, your on current drops down, right. So, increasing threshold as well as dopant freeze out, right. So, these are very, very important phenomena here. If you look at the last point which is mentioned here, the band gap actually widening makes the threshold voltage go high, right. Dopant freeze out, whereas in the other sense is that, what is the meaning of dopant freeze out? It means that not all the dopant species which you have entered into the device or into the structure is not able to give all the electrons to the conduction band, right. So, if you have 100 species or 100 sets of donor species you have inserted, maybe 7 or 8 of them have actually gone to the conduction band, right. So, these two are two competing mechanisms, the dopant freeze out and the band gap widening. Band gap widening helps you to increase the threshold voltage, whereas dopant freeze out tends to decrease the threshold voltage, and you need to find out how therefore the threshold voltage is a function of these two. With this basic background, let me deep dive into a few slides which are not populated earlier. I will be writing down it for you, and so that it's a one-to-one conversation. This discussion is taken from a research paper, which is basically a research paper which was published in a conference, an IEEE conference, and I just wanted to give you an idea. This is basically a paper by Christian Enz, right, Enz, and the authors are Becker, and then there is Farzan. So, these are 3 authors of paper, and this is a research paper which I am referring to, and this is basically a cryogenic electronics or cryogenic threshold voltage development, right. So, I am developing a model for that, right. That's the whole idea behind this research paper is all about. Now, why is it important to study threshold voltage? I will just give 2 lines and then we can move forward. You see, if you remember very well during the early few lectures of this coursework, that your qubits, right, your qubits which is basically responsible for doing all sorts of computation, right, they are actually stored at millikelvin, right, and your underlying electronics are all kept at say some Kelvin, say 4.2 to 4.4 Kelvin it is kept. So, at such a low temperature, even if you want to maintain such a low temperature, your power consumption should be as low as possible for the CMOS circuitry. And the idea here is that typically what people have reported is that a power consumption of 1 watt, right, at 4.2 Kelvin is an acceptable limit. So, you see the consumption of power is relatively small, is severely limited, because you are somewhere very close to low temperature region. At the same time, one important point is, you not only your power consumptions have to be becoming low, you have to also meet the timing constraints. What is the meaning of timing constraints? And I will give you a brief idea to do that, because those who are not initiated, especially those who have not understood or those who have not gone through a course on digital VLSI design will not possibly understand it, but give you a very brief idea so that it is clear to you. Let us suppose I have a clock, right, I have a rising clock and I have a edge triggered design, which means that during the rising edge of the clock, let us say a flip flop, the data is accepted by the flip flop, or it is also known as sampled by the flip flop. So, this is known as a positive edge triggered design, right, positive edge triggered. Now, if it is a positive edge triggered, it effectively means that when the clock is rising, it accepts data. However, one important point is that the data should be held stable some delta t, right, before the rising edge of the clock. The data should be stable, otherwise data can be unstable, but somewhere here the data should be stable, a fixed value of data should be available. This time is referred to as a setup time of a flip flop in digital logic design. Now, please understand that not only your power consumptions are low, but there is a serious constraint on the timing, which means that the data has to be held stable before the rising edge of the clock. The clock should not give you a very large power dissipation, the flip flop should not give you a large power dissipation, so on and so forth. Fine, you should be aware of all these things, because that is the sort of a underlying challenge of a cryo computing system. There were 2 things which is happening. One is of course the power, and the second is timing constraints. These both are sort of constraints, and these both are possibly affecting the device itself. Now, let's take up a basic idea and show you what do I mean by that. There is something known as overdrive over the device, right. This you possibly know also. Overdrive is given as VDD or VGS minus VT, where VT is the threshold voltage of the device. Higher the overdrive, more will be the current, right. So, in a MOS device, if you give, let us suppose VGS equals to VDD, right, VGS equals to VDD, then I get overdrive to be equals to this much, VGS minus VT. Now, you see your VGS is fixed, but if you go on increasing the value of VT by reducing the temperature and following the Varshni model, VT is increasing, then the overdrive actually starts to decrease, overdrive decreases. Why? Because the difference between VGS and VT actually becomes lower and lower. When the overdrive drops down, the current actually starts to fall down. And not only that, please remember, in a FET device, if you remember, ID is proportional to VGS minus VT whole square. So, if VGS minus VT overdrive falls by say half the value, ID will fall by quarter value. So, it will fall to 1/4 of its initial value. So, that degradation is relatively very large in cryogenic design in a sense. So, and therefore, you are playing with two important points, that your overdrive has actually dropped down, power consumptions have to be very low, and you are limited by the timing constraints which are available to you. So, what people did, and over a period of time this paper was meant to do that, was to look at a 28 nanometer CMOS technology, and this 28 nanometer CMOS technology, they took four NMOSs, they took 4 NMOS devices, and what they did was they took into what is known as a Lakeshore cryogenic CPX cryogenic probe station, right, which is maintained at approximately 4.2 Kelvin, and they inserted there, and they increased the temperature step from 20, 36, 50, 77, 110, 160, and then finally 210, followed by 300. So, this was the increase in the steps of the temperature of the cryoprobe station, and they measured the IDVG, the drain current versus gate voltage, and IDVD for the device to be in the linear region where VDS is very small, as well as in the saturation region where your VDS value is very high. So, the experimentation was done in the linear region where VDS was maintained to be approximately equals to 5 millivolt, and it was also done in the saturation region where VDS was maintained at approximately 0.9 volts, correct. Try to extract the value of IDVG. From IDVG, they were able to extract the value of the threshold voltage. So, that was the procedure that they adopted in this experimental paper in a sense. Now, apart from that, they also studied therefore the threshold voltage, they studied DIBBLE, drain induced barrier lowering, a second order effect or short channel effect in a MOS devices because of cryogenic temperature, right. We will come to the band diagram later on, because that is there in the later part of the discussion, but let us look at the vacuum level energy level, right. So, we define one important term, and that term is given by psi, a potential, and is given as EI minus EIB divided by Q, where Q is the elementary charge which you see, right. This EI is referred to as an intrinsic energy level, right, and EIB is the intrinsic energy level, where in the bulk. So, this is at the interface silicon dioxide, and this is the bulk, right. If you subtract the difference between them, divide by Q, you get the surface potential or the potential at that particular point, energy by Q, because E equals to Q into V, Q gets cancelled out and you are left with V. So, this psi is sort of a potential at this particular point. Now, let us look at the concept of band gap widening from the viewpoint of Varshni model. So, first we look into the band gap widening, right, at cryogenic temperatures. Now, what we have seen in the earlier stages also, that 1.12 to 1.17 EV is the increase in the band gap EG as you reduce the temperature, right. Now, if you now look at in a much more detailed manner, if you want to look into it, deep dive into it, then you will see that the occupancy function, remember the Fermi potential which we had earlier talked about, which is F of E, the probability of finding electron is half at T equals to 0 Kelvin at the Fermi potential energy. That is what I was talking to you. This Fe value, if you remember, is a function of temperature. Remember, it was Fe was equals to 1 over 1 plus exponential E minus EF by kT, right. So, if you go on decreasing this temperature to a very low value around 0 Kelvin, this possibly will obviously shoot up exponentially high, which means that this will shoot up, this will go down, and therefore, the Fermi energy itself will scale down to a very low value. Fe will go down to a low value. Now, if you are looking into the Fermi potential, that I can correlate with the band diagram here. So, let us look at the band gap widening concept, right, with the Fermi potential coming into picture. You see, this is my metal. So, this is my metal, this is oxide, this is semiconductor. Q phi m is my work function at the metal work function at the metal side. EFM is the Fermi potential, which is inside the conduction band of a metal. This is the vacuum level, where vacuum level is the level where the energy required to go there is very high, and all the energies below are negative, because negative energy implies that it is a bound state. Now, if you look very carefully, if you look at the first diagram here, this is at 298 Kelvin, right, and this is for the p type silicon, and this is 4.2 Kelvin. Since it is a p type silicon, my EF, the Fermi level, is very close to the valence band, and my acceptor level is between the Fermi level and the valence band. Now, you might understand that at 298 Kelvin, complete ionization will take place, and you will have large number of holes available to you at 298 Kelvins, at 298 Kelvin. So, now if you look at the Fermi function at this particular point, then you see that the Fermi function comes like this, and it then bends like this, and then it comes like this, right. This is the energy scale which I am talking about, which effectively means that the Fermi level potential is almost 0 at the top above the conduction band. So, you will not find any free electron there at T equals to 298 Kelvin. Now, and that is the reason you see that your Q phi f is approximately equals to Q phi f star, which means that there is almost no change in the Fermi potential, and Fermi level is almost very close to the valence band. 100% ionization has taken place, and this is, we have not given any bias. So, therefore, there is no band bending. This is known as a flat band condition, and I am maintaining that. Now, let us come to the right hand side, right. The right hand side picture shows you the p type silicon at 4.2 Kelvin, excessively low value, right. Now, if you see very carefully, you see these are white dots, white circles, primarily meaning that they are accepting the EA level, is accepting the electrons from EV and itself turning into holes. So, these white circles are basically the holes. So, large number of holes are available. Just compare that with the 4.2 Kelvin case. Since the temperature has fallen down drastically, so the amount of energy given is kT by Q, right, kT by Q. This T has fallen down to such a low value that is not even enough for the acceptor ion to accept any electrons, and that is the reason you see these are all black circles which are coming up here. These are all black circles, which primarily mean that electrons have not been promoted from the valence band to the acceptor ion, and therefore, there is not been generation of large number of holes available to you. However, you see one important point here, that there are two terms here, EF and EF star. EF is the Fermi level which was happening at the T equals to 300 Kelvin. However, this EF star has changed, the Fermi level position has changed. Why? By the same principle which I told you here. You see, if you look very carefully, T decreases, this increases, which means that this decreases, Fe decreases, right. Therefore, there is a change which is happening in this case, right. So, what is happening? This is my Eg, and this is my Eg at T by 2. This is Q chi electron affinity. This is my metal work function. This is my Fermi level, and what has happened is effective Fermi level and the original Fermi level, there is a change, and that change is approximately equals to Q times del phi f, where del phi f is a change in the value of the Fermi level. So, the energy change is Q times del phi f, fine. So, what we have learned from all these discussion, at least for this basic discussion, is that we have been able to formulate at least this one important point, that at ultra low temperatures, where you are reaching the cryogenic temperatures, at even at flat band, you do not have 100% ionization, and there is an effective Fermi level which is quite different from the real Fermi level, right. That is what we have learned from here. Let us go back again to the basic discussion here. So, there are two things which will happen. There will be a band bending which will be there, and then there will be also a Fermi level change. Fermi level, if you see, has gone up. Gone up basically means that the probability of finding holes has gone down at the valence band, right? And these two phenomena which you see tend to change the value of the threshold voltage drastically, right? That is what we have learned, or we know from that basic idea here. The takeaway therefore is, please understand, is that the intrinsic carrier concentration will now decrease, widening of the EG will take place, threshold voltage will increase. Okay. Now, if you go to the second phenomena, because of, then we could, what is known as an intrinsic carrier density scaling. So, the you remember at T equals to 300 Kelvin, the number of carriers, intrinsic carrier concentration is 10 to the power 15 per centimeter per meter cube, right? And as the temperature goes on increasing, this value goes on increasing because of a large EHP generation. However, if you look at if you go to deep cryogenic temperature, the intrinsic carrier concentration Ni, right, has an exponentially dependence on Eg and 1 by T, minus 1 by T, actually plus 1 by T. And therefore, as the Eg widens and Fe scaling strongly decreases. So, if you see, Eg will widen, right? Eg will widen for Varshni model which we follow, and there will be, obviously, temperature goes down. So, both help you to reduce the value of Ni, intrinsic carrier concentration. So, the intrinsic carrier concentration also decreases with increase in temperature, right? That we have learned in this case, right? So, I think let me stop here today and recapitulate what we did, and then we will take up the next two phenomena and then the threshold voltage idea in the next lecture. What we did today was give you an idea about the model for bandgap widening, related the bandgap widening with the number of carriers available to you, and therefore the change in the threshold voltage. What we will do subsequently is we will take up two more phenomena here, and that is the increase in the bulk potential, and we will come to incomplete ionization of electrons and holes, and incomplete ionization because of electric field, and then we will go to the threshold voltage model in the next class. I hope you enjoyed it. Thank you very much.